Let us start. So, at the end of the last class, we had studied the following product of operators. J A of Z. Remember, we are studying an SU2 Wessel-Witten, an SU2 Kac-Moody algebra, SU2 Karuth. So we looked at J of Z1, JB of Z2, and JC of Z3. Okay. And we looked at the product of these three operators and first asked ourselves, what can we say about the terms in this product that are singular when Z comes either to 1 or to 2? Okay. So our strategy was we would, we were interested in we're going to be interested in 1 and 2 very close together and then 3, so as to try to make this Sugawara stress tensor. But the problem with that was that we couldn't then use the OP between this and this and this and this, because 1 and 2 were closer to each other than 3. So instead we looked at the general product, isolated out all terms that were singulars when 3 went either to 1 or to 2. They're going to be the same point eventually. And then after that we were going to do an expansion in 1 goes to 2. Okay. So the obvious statement was that all singularities as 3 goes to 1 are, let's see, so there's K epsilon A, B, epsilon. Now we should be careful about the order. Okay, so our rule was J A of Z, J B of W was K Z minus W, the whole thing square, plus epsilon A B C J C of Z minus W. JC, and this JC is at W. Okay, so here we have Z. This in that rule, this is Z, this is W. For instance, so we get K divided by Z3 minus Z1, the whole thing squared, and that's just for the 1, plus then epsilon CAB JB of Z2 divided by Z3 minus Z1 and CAD Z3 minus Z1, right? Plus K divided by Z3 minus Z2, the whole thing square, plus epsilon CB, let's say D, JD of Z2 divided by Z3 minus. Yes?
So we are essentially interested to put that down where we are taking with Z3 with Z1 and Z3 with Z2. The reason why we are doing this is it because in the end we cancel, taking out all the divergences coming from Z1 coming from Z2.
Right. We know what our definition is. Right? We know what our operator, the operator we want to do. It's JJ 1 goes to 2 minus K by Z12 squared times sum over A, dimension of the group, 3 in this case. Okay. So we want to identify the OPs between this operator and JC3. Okay. Now, what do we want? What does it mean that we want the OP? We want all singular terms when J3 comes towards this operator. But we can get that by finding all singularities when J3 comes towards either 1 or 2, and then fusing 1 and 2, expecting that in that fusion all that will be left behind is this normal ordered operator. Okay, so see how it goes as we go along. Okay, so this was our result. Is that clear? Okay. Now all we are supposed to do is take this result and now take 1 to 2. Now we have to do it carefully. We want to keep all terms that are all terms that are up to order 1 as 1 goes to 2. Any term that vanishes as 1 goes to 2, we're not interested in keeping. A term that is divergent when 1 goes to 2, we want to keep. And a term that is finite but not 0 as 1 goes to 2, we want to keep. Okay? So let's do this term by term. JA, thank you. Okay, so let's do it term by term. Let's first do the terms with the k's. And these are the easier terms. Okay, they're easier because they have only one j, so we don't have to do a further operator product expansion. Okay, so let's do this one by one. Let's see. In this term, now Z3, as far as when we're taking 1 to 2, Z3 is some finite object. Okay, so in the term when we take 1 to 2, okay, or let's say we take 2 to 1, let's say we take the limit 2 goes to 1, here we can just replace Z2 with Z1 because the higher order Taylor expansions will be proportional to Z21 and so vanish as 1 goes to 2. Is this clear? Okay, so these two terms are very simple. We just get 2k divided by Z31 the whole thing square because 2 has gone to 1. Thank you, thank you, thank you. Delta, this was a BC, AC, and this was a delta, BC. And so really I have this, but in the end I'm going to be taking those two equal. So, but you're right, at this stage we have it. Yeah, we have delta AC plus delta BC. Thank you. Okay, excellent. Okay, now let's attempt at the terms that have no k in them. So this term and this term. Here we have to be more careful. We have to be more careful because when we take this to this, okay, there will be singularities in the OP, and then we have to be careful about whether this is 1 or 2 because we have to do the Taylor expansion. Okay, so we're going to take 2 to 1, so the easier term is this guy because here this was already a 1. Okay, so let's write that out. So that's plus a epsilon CAD. Okay, now we're taking 2 to 1, so we get another epsilon BD, let's say M. Let's first take the singular. So the first term was K delta of BD and then Z21 the whole thing squared. Okay, plus then we take this guy to this guy, that's the epsilon term, so that was epsilon B D, let's say M J M at Z1 and Z21 the whole thing to the power 1. All good? Okay. We are going to make sure all our operators are evaluated at 1, so we took 2 to 1 and that worked. Okay. Now in the next guy, and this whole thing was divided by Z31. This whole thing had this factor here. Okay. Now in the next guy we do something similar. Okay. So we write epsilon CBD BD divided by Z3 2. Okay. Then now we will take, let's once again take 2 to 1. So the operator on the upstairs becomes 1. So we will take so this is delta dA Z21 the whole thing squared plus epsilon dAm then we got epsilon dAm, then there's Jm of Z1, the whole thing divided by Z21. All good? Exactly, that's the next step. That's the next step, as you say. So, as Rajat wants, we will take this behind. We'll call this epsilon C, CBD. And now we're going to need the Taylor expansion of this up to second order for this guy, and up to first order for this guy. So let's work out the Taylor expansion. So this is 1 over Z31. So Z3 minus Z1 plus Z1 minus Z2. So it's 1 over Z31 plus Z12, or Z31 minus Z21. Okay, so we can write that as 1 over Z31 into 1 minus Z21 by Z31, which is the same thing as 1 over Z31 into, and then open bracket upstairs, 1 plus Z21 by Z31 the whole thing squared, whole thing plus Z21. Okay, and we will put that in, insert this into here. Okay, and then we just group terms. So we have terms that upstairs there that are constants, and terms that have a j. So let's first deal with the terms that are constant. Okay, and here there was a k, sorry. There was a k, okay, good. So let's first deal with the terms that are constants. Which two, sorry, where?
1 by Z.
Haven't we taken that into account upstairs? Yeah, the top line was those guys, right? So there was this plus that plus that. Okay, excellent. So let's look at the constants that come from there. That was just epsilon C A D Z31 into K to Z21 the whole thing squared. Nothing to do here, right? The constants that come from here are so plus epsilon CBD. So let's first take the leading order term. Epsilon CBD, in the leading order term, this is just Z31 again. Z31, and this is Z21 the whole thing squared, and this has a K. Now what is this BD? Sorry, where are we? What have I missed here? I took this. D was, I'm sorry, so I was this one, epsilon D. Okay, with a delta D, dA. Of course, there was a delta dA. Right. So this one is just the delta tells us that we replace D with in the first term, where were we? The delta tells us that we replace D with B. So this is CAB. Okay? And in the second one, the delta tells us we replace D with A. So this is CBD, CBA. And these two are equal and opposite because epsilon is completely antisymmetric. Okay? So this funny leading order term just cancels. Is this clear? Okay? So now let's move on to the other terms. The other terms, you see, right, let's move on to the other terms. So the other terms, let's take the first subleading guy from here. You have a class? Ah, okay. Okay. Excellent. So in that term there, you know, this funny term, that guy is gone because it's cancelled against the leading order term here. But there are two subleading terms here from the two terms in the Taylor expansion. So the two subleading terms are simply this guy, but with extra powers. So what's left is epsilon CBA times now Z31 Z21 plus epsilon CBA Z31 squared and plus Z31 cube and without a Z21. Is this clear? And then there is the K. Okay? Now this term would have been there and these terms would have been there and would sort of been quite funny terms. But we are going to be interested in A equals B. We're going to be interested in taking the two J's, JA, JB, and setting them equal to each other. Okay? And so just for that reason this term goes away. Okay? On the other hand, the other constant terms that were up there, they survive when we set A equals B. Okay? They survive when we set A equals B and just become sort of equal to each other and they're going to stay. Okay? Excellent. So, and we'll see what the meaning of that term. That will be basically absorbed into the normal order of a normal order of our thing. Okay. So as far as constant terms are concerned, this is what we get. This plus that. So let me write down the full answer anyway, just since we worked it out. We get K Z31 the whole thing squared into delta AC delta plus delta BC. And that whole, sorry, what am I saying? And that had J, yes. Yeah. So these were of different type, which you could also have seen from dimensions. Right? These had one extra. Yeah. So this thing came with a J B of 1 plus this thing came with a J C of Z2. J B of 1 and J A of what? Right? Is this right? Thank you. Delta. Plus delta, what was it? BC. J B J. Thank you. So this was not even a constant term. This was a J term. This was a term that was one of the terms that has just a J in it. Okay, so this term is there. Then there was a constant term which was this guy, epsilon C B A by Z31 the whole thing squared, Z21 plus epsilon C B A divided by Z31 whole thing cube, and this is going to play no role because we're going to set B is equal to A. Okay, excellent. Yeah, so more accurately than calling them the constant terms, these are all the terms proportional to K. Okay, great. Now let's look at the terms that are not proportional to K. So the terms that that involve two epsilons. So there was that term with two epsilons and this term with two epsilons. So let's look at them one by one. So let's look at this term with two epsilons. So that's epsilon. First, what do we have to do? Here, this was already Z31, so there's no Taylor expansion needed. So it's just what it is. It's epsilon C AD epsilon B dm by Z31 Jm Z1 by Z2. Okay, and then underneath it there is this other term which was epsilon C B D, and now we'll keep this Taylor expansion. So let's keep the Taylor expansion. So there's 1 over Z31 into 1 plus Z21 by Z31 into epsilon CBD, okay, epsilon CBD, and then epsilon DAM JM of Z1, that's good, and over Z21. Okay, so the sum of these three terms, this, and this, are the remaining terms that are left behind. In our Taylor series expansion, in our operator product expansion. So let's first take this leading order term, this guy, and compare with this guy. Okay, so those two terms are epsilon CAD epsilon BDM Jm of Z1 by Z31 Z21, and both the denominators are the same in both of them, and here we have plus epsilon CBD epsilon DAM Jm of Z1. Okay, now let's look at these guys. Both of them have a D contraction. Both of them have the following structure. One of the indices here has an M. This index is contracted with the index of this guy. This second index is contracted with the third index of this guy. Okay, and so okay, fine. So since these epsilons are contracted, we can make it product of deltas, right? Since they've got a contracted index. So this guy, so let's move this guy cyclically. So this is same as epsilon MBD. Okay. Now these D's are contracted, so this thing is delta CM delta AB minus delta CB delta AM. Okay, contracting with JM. Okay, Whereas this guy, we perform a similar manipulation. The manipulation will cyclically move this so that this D is here, and that becomes delta C A delta B M minus delta C M delta B A hitting J M of Z1. Okay, now this is delta Cm, delta AB. These two are the same but equal and opposite. Okay, so this term is there. Is this clear? Okay, so all that remains in this term is the guy that comes from the this subleading expansion. Is that clear? All good? I'm sorry about this algebra, okay, but one of these I thought I would just do on the board. So I can't remember the last time I've done this algebra, 20 years ago. It was just for my own sake also. Okay. Okay. Which one? Delta Cm, delta AB? Oh. I made a mistake somewhere? Yes. Yeah, thank you. Thank you. So this one, so this, you say one of these terms just completely cancelled, right? Which one? This was first and fourth. These completely cancelled. And these guys, so let's write it down. We'll get something plus, thank you, Raghav, thank you. So CBAM, we get delta CABM delta CB AM by Z, this was Z31, Z21. And with the JM, of Z1 here. This was there, but as you said, it's going to cancel when we set A equals B. It's not going to be important. And what remains then is this guy, which was 1 over, now the Z, 3 1s have become 1 over Z, 3 1 the whole thing square, and then the Z2 1s have cancelled, and then we get epsilon CD. Now this was, once again we do this manipulation, so let's write in terms of deltas. So we will get delta CA and delta CA delta B M minus delta C CM delta AB. Right. And this also multiplies a Jm of Z1. Okay, so we'll add this here. I wish this board would also. Anyway. So we will also get plus 1 over Z31 the whole thing square delta CA delta BM plus delta AM delta CB JM of Z1. Sounds good. Okay? Okay. Excellent. So let's write down our net answer and then we'll try to make sense of it. Okay. So what did we do? We took this triple product. We took this expansion where you kept keeping all terms which were singular when 3 went to either 1 or 2. And then we also expanded 1 goes to 2. Okay, so in the end we only have two remaining positions left, Z3 and Z1, because 2 has been replaced by 1 everywhere. And so our final answer is the sum of these guys. Now let us set A equals B, and later we'll do the sum over the rank of the gauge group. Let's set A equals B. Once we set A equals B, this guy becomes what? This guy becomes B. What was C? Was this a J? B. This was delta B. Okay, so we set A equals B. Okay, and let's write the sum. So we set A equals B. So we have, so now we have sum J A of Z1, J sum over A of Z2, and then this limit Z2 is equal to Z1, all that way. You know what we're doing. JC of Z3 is equal to, so we get the terms first with involving K. So there's K, and now we get JC of, because there's this first A is B, and then we're summing over everything, so there's just JC, and there's this factor of 2, right? 2K JC divided by Z3 1 the whole thing square. That's the first term. Okay. Now there was this second term which was just 0 CBA, have I written it wrong? A equal to B, that's it, fine. So this was just equal to 0, thank you. So this term just doesn't contribute because A is equal to B. This term also doesn't contribute because A is equal to B. Okay, this term contributes. Okay, and so we have plus 1 over Z31 the whole thing square, 1 over Z31 the whole thing square, and then now what do we get? This M is contracting here, so M here can be replaced by B. So let's write this out. This was delta C A JB. M here was B, and plus here delta CB JA. And then we set A equals B and do the sum. So we just get C. I mean, so A is equal to B and we do the sum, so it's just JC. And is there some, what does JC mean? C was there, yeah, so it was just C, JC. So we get JC of Z1. So, which, sorry, here? Yes. Delta C, sorry, let me make sure. So, M is a, are you saying I wrote it wrong? Thank you. CM, and this was AB. Thank you. Okay, so let's see. So, first term, so let me just write it again. So, here when I did this, I got M was B here, and then I did this sum, I set A equals B and did the sum, so I got JC. Okay, so this term is okay. Now let's look at the second term. As you say, this M was C, so I get JC, and I have now a sum over, I said A equals B and I have a sum over A and B. Okay, so that's good. So I get JC, but with a 1 plus And in this case, this is just 3, right? Because A and B run, because we're doing SU2.
There should be minus sign, right?
Minus sign. Second term, minus. Yeah?
It's 1 minus.
1 minus 3. Minus 3. That's it. Yeah. There was a minus sign. Thank you. Minus sign is a bit, maybe a bit odd. Okay, fine, let's see. Now we put these two together. So this is 1 over z 3 1 the whole thing square into 2k plus 1 minus 3. 1 minus 3 jc of z1. Okay. Now you know, I hope this normalization, I hope we haven't messed up on the normalization, but let's come back to that point. The important point here is that this thing is a number. Okay? If we had a stress tensor and it was acting on a current, T of Z3 on J of Z1 would have been 1 because it's H is 1. So 1 by so J of Z1 divided by Z31 to the power 1 plus del J squared plus del J Z1 to Z31, and this number would have been 1. Okay. So where have we, have we somewhere set 2 equals 1 carelessly? Right. Where was that? Somewhere here, when we had a Z2 at this point, okay, no, that's okay. The question is, have we set, okay, so the two things that we were supposed to get a number times this, but we were also supposed to get right. Where did we miss the derivative? Just a minute. Right. If as you say, if JC was evaluated at Z3, so where maybe we messed up on where these J's were evaluated. Let's see. First, I'm so sorry. Give me a minute, we'll figure out where we messed up. So first thing I did was to take this and look at all the singular terms. That was okay. That was okay. We never had a J of Z3 as you suggested at this stage. If we had a Z21, one of these subleading terms.
What Omkar is suggesting is the final expression
is correct. You just expanded now not about Z1 but about Z3.
Because JC of Z3 is what we have on the left hand side.
So the left side is big.
No, I mean sorry. So we are
This expression just interchange Z1.
Yes, let's look at T of Z1, J of Z.
but what do we expect from this?
Because that
Oh, you're saying I just identified it wrong. Thank you. Yeah, our T was located not at Z1 but at Z. Thank you so much. Yeah. Okay, this was T of Z1, J of Z3. Okay, that what we wanted was, what we expected was, thank you. What we expected was 1 J of Z3 divided by Z1 3 the whole thing square plus del J at Z3 divided by Z1 3. This is what we expected. But you're saying we've evaluated everything here at Z1. Okay, and therefore once we make this number 1, just the Taylor expansion as you pointed out will automatically give us this del J, because it will just be the plain Taylor expansion. Okay, so all that remains is to make this number 1. Okay, so this number is made 1 if we just take whatever this number is, let's call it some alpha, and we identify T with sum over A J, okay, divided by alpha. Okay, so thank you both of you. Okay, so we identify T with sum over A J divided by alpha. Okay, and then this expression here has exactly the right form as exactly the right form as we would expect for a stress tensor. Okay, so this expression here is exactly the form we would expect from a stress tensor, and so it's plausibly then a stress tensor. Okay, so now let me see if now let's look at the number. I hope we got that one right. I hope I can find it somewhere here. Okay, we've got 2k, which I think our k was a half integer. So 2k is what other people will call k, plus h of g psi square. Psi square is probably 1. H of g, what is it? H of g? Okay, h of g plus 1 is dimension of g plus rank of g, divided by rank of g. So h of g plus 1 is in SU2 case, dimension of g by rank of g is 3. So h of g is 2. H of g is 2. What Polchinski reports is k plus 2. His k, so our 2k plus 2. Our 2k plus 2 plus 2. Just let me check that once more. Okay. Could it be we've made a minus sign up there, mistake up there? With the, which one? We got one with a minus and one with a plus. Could it be that thing should have been swapped? Can I request you guys to go back and check this? Okay, I suspect we've swapped the minus sign here. I suspect we've swapped the minus sign here, and then we will get this 2k plus 2, this famous 2k plus 2 that appears in SU2, what people will call k plus 2. Yeah, this, by the way, this shift, so as you will see all over the place. So let me work, in the last lecture we called this 2k k tilde, and in this SU2 context we got k tilde plus 2. This quantity is often called kappa, shifted level. It appears in many formulas in Weissenberg-Witten theory, and the analog of this will be kappa tilde when we are doing SUN, as you will see, as we will explain, but just the kappa will be kappa tilde plus n. Okay, it's this shifted level that appears, as I mentioned in many formulas, will play a role in determining, for instance, the dimension of operators. Okay, I'm sorry about this minus sign. I'm going to request you guys to track it down. Okay, but the answer other than that is the correct one.
This is because of the current, because they are in the current series?
What do you mean?
I mean, what do you mean by first k tilde plus n? This, what is this n?
N is for SUN. So suppose we were working with SUN current algebra. The shift would be, k is what appears in the JJOP as the coefficient of 1 by z square. Okay, but this shifted k, this kappa, appears in many formulae. So what formulae? Okay, so let's take another example. Okay. Another exercise one can do, is the following. One can look at the OP between a primary operator, phi I of z, let's call it z3, this is the analog of what we called it here, ja of z1, jb of z2. Okay, so now the exercise we can do is to look at this OP, I mean this product of three operators, and once again keep all terms that are singular as this guy goes to this guy and this guy goes to this guy. Okay, once again keep all terms that are singular as these two guys go to each other. Okay, and then take the fusion of and then take the fusion of 1 with 2, very much like we did with the current. Okay, if this guy genuinely was a stress tensor, what we should recover is the operator product of the stress tensor with an operator, and one might guess that since it was primary under current algebra, it would also be primary under Virasor. Okay, so one might hope to recover the OP of the stress tensor. Okay, one might hope to recover the OP of the stress tensor with a primary operator. In fact, this calculation would be easier to do. I'm not sure if it's actually worth doing because what is to be done is totally clear, right? It's just imitate the analysis we had before. It's easier to do because there was no analog of the z squared, 1 by z squared when we took j with j, right? This guy with this guy only has a 1 by z12 singularity. This guy with this guy only has a z12 singularity. Now remember that the singularity of this with this is governed by the representation matrix of SU2 in which T transforms. Okay, so when we take this the singular term here, we will get another phi with a representation matrix, right? And And then when we take this guy to this guy, okay, when we take that fusion, this part, this guy would already become a phi. So we'll take another fusion of this with this, which will give us another OP of T with phi. So you'll get a second representation matrix. Because we're actually interested in A is equal to B, both of these representation matrices will come with an A. And because there's a sum, they will come with a sum. And because we've divided this TA, this sum over things with this k tilde plus 2, that will also come with a 1 over k tilde plus 2. I believe if you do it carefully, you get, so what we will get is sum over TA by kappa. So what we're going to get is that we do the same exercise for current operators, for primary operators. We will get T of Z with phi I of, let's say, W will be equal to sum over TA. This is in the representation in which phi lives. Okay, so I could call it TAI if you want, in that representation. Okay, divided by Z, divided by Z1, Z minus W, the whole thing square, times phi plus del phi by Z minus W. Okay, and it could come with a number. I can't swear that there isn't a 2. I can't swear that there isn't. If there's a number, it's a half or a 2. It could come with a number. Okay, so I'm going to encourage you guys to do this calculation as well. Okay, but the structure is sort of clear. Okay, yes.
Yeah. So in these current theories, we have sort of constructed this stress tensor, right? So can we say something about the action of what kind of action does this stress tensor represents? Like of which theories? Can we say something about that? Because it is just from the OP we have constructed this T, right?
Yeah.
Can we say something about the action?
So this stress tensor acts on all primary operators that are charged under primary in the Wessumino-Witten sense, primary in the current algebra sense. Okay, what this equation tells us is that if you had a primary operator in the current algebra sense, the action of this stress tensor on it is exactly like the action of a stress tensor on a Virasoro primary with the dimensions. So hang on for 2 minutes. This is where we're going. Okay, at the moment we've just done algebra. Yeah, exactly. So what the answer to your question is what we're coming to next. Okay, so we get this object. So as Rajat asked, okay, what this tells us is that every time we have a current algebra primary, that object is automatically also a Virasoro primary. Okay, and it's a Virasoro primary of a given weight. Okay, the weight is given basically by this quadratic Casimir divided by 2 times kappa. That's the standard formula, where quadratic Casimir is just TA, perhaps by 2. Okay, whatever people call quadratic Casimir. Okay, it's given by quadratic Casimir by 2 kappa. Okay. Okay. Now, your question, Rajat, is what does this mean about some transformation? Well, this is a good question. Let's suppose that phi was a scalar operator. Okay. Let's suppose that phi was a scalar operator, by which I mean it had the same h as equal to h bar. We've not talked about the anti-holomorphic part, but let's imagine that there's also a current algebra in the anti-holomorphic sector, and phi transforms the same way, same representation under the anti-holomorphic current algebra, and we make a stress tensor which is the sum of the, so this is called, by the way, the Sugawara construction. this construction of a stress tensor out of current algebra is called the Sugawara construction. This phi transforms with the same weight under H and H bar. Let's suppose that. So then this is a scalar operator which has a weight H. Okay, now what does it mean? Let us remember the early part of our course. In the early part of our course, we asked ourselves what conformal transformations were. And we answered it by saying a conformal transformation is a diffeomorphism, a conformal diffeomorphism, followed by a compensating Weyl transformation. A conformal diffeomorphism is a diffeomorphism that changes the scale factor by a certain amount. Then we do a Weyl transformation to undo that scale factor change. And so what we are left with is a theory in some metric is related to the theory in the same metric. Now, these product of these two transformations was what we called a conformal transformation. Okay. Now, how does a scalar transform under diffeomorphisms? Well, by definition, it does not transform. Of course, it transforms because its coordinate moves. We're not counting that. Okay. So when we say that something is weight H under conformal transformations, what it means at the fundamental level is that this is the weight under Weyl transformations. If you go back to the notes of the first part of this course, we made this very precise. We got the exact relationship. What Weyl weight corresponded to what scaling dimension, whether it was plus H by 2, I can't remember. Okay, right? So what this tells us is that if this is the stress tensor, in the sense that if this is the stress tensor, in the sense that this is how the theory couples to a change in the metric, then our operator has a given Weyl weight which is given by this. Now the question of whether this is the stress tensor or not, in the sense that is this how the theory couples to change in the metric? Let's come to that question. You see, suppose you tell me no, this is not the true stress tensor. The true stress tensor is something else. Okay, so the true stress tensor is T Rajat. Okay. So I've got this trial stress tensor. Okay, let me say one more thing before that, just one more thing. The last thing I wanted to say was the following. The last thing I wanted to say is that there's a third exercise that you can do, which is take JA, JB, JC, JD. Now, and let's look at these as Z1, Z2, Z3, Z4. Now we do the expansion such that we keep all terms, first keep only those terms that are singular when either 1 or 2 hits either 3 or 4. Then take the expansion, 1 goes to 2, 3 goes to 4. And set A equals B, C equals D, do the sum. Okay? This is the operation that will give you the operator product of two stress tensors. Okay? This kind of thing is hell on earth to do. Actually, what you can do is use the fact that we've already found the OP, do this first. Then we've already found the OP between T and 2 J's. So you can simplify your calculation that way. But anyway, you do this and you find that you get T of Z, T of W is equal to what was our stress tensor? C by 2. C by 2 Z minus W to the 4 plus 2T Z minus W, the whole thing square, plus del T Z minus W, with C is equal to, in this case, 3K divided by K plus 2. That K plus 2 in the denominator is the same K plus 2. Oh, I'm sorry, this is K tilde. This is what everyone else uses. 3k tilde divided by k tilde plus 2. That k tilde plus 2, the denominator is the same k tilde plus 2 that we had, that we've seen already. And then you get this 3k. Okay. Excellent. Excellent. Okay. So what we have is this thing behaves like a stress tensor. Now, suppose Rajat had another stress tensor, which was the stress tensor that, from some deeper consideration he's figured out is the thing that actually couples to the metric of the theory. Okay. Now, Rajat's theory has a current algebra. So it's got these currents, and out of that we can just by hand construct the Sugawara stress tensor. Okay. So we also have T Sugawara. Okay. Let's take the difference between T Rajat and T Sugawara. Okay. Since T Rajat has the same OP with the stress tensor, since T Rajat has the same OP with the current that T Sugawara does, by definition, the OP between these two and JA will be no singularity. Is this clear? Okay. What this is suggesting is the following. It might be that you've got, another kind of notion of stress tensor, but because this other thing, as far as the currents of the algebra are concerned, this other thing is the same as Sugawara stress tensor. What it's suggesting is the following: that you've got a sector of the theory in which current algebra, which is like the current algebra sector, and maybe something else that is, roughly speaking, decoupled.
To this current?
Decoupled in the sense that the stress tensor that you make out of it. So let's imagine the T Rajat minus T Sugawara is the other part of the stress tensor. So one example would be, suppose I had a Wess-Zumino-Witten model plus a minimal model. The CFT is the sum of these two. Okay, in that sector, in that theory, okay, my operator, my stress tensor would not be just given by the Sugawara construction, because the Sugawara construction gives me the stress tensor for the Wess-Zumino-Witten model. Okay, it doesn't give me the stress tensor that's the minimal model. So the full stress tensor there would be the sum of Sugawara plus the stress tensor for the minimal model. Okay, and the full stress tensor minus the Sugawara stress tensor, which would be the minimal model stress tensor, would have non-singular OP with the currents, as we've demonstrated here. Okay, so of course this is a question you have to really answer theory by theory, but this is how it's going to work. For instance, in the Wess-Zumino-Witten model, the Sugawara construction correctly computes the stress tensor. This is something you can check from, the Lagrangian. Okay, and because now if you've got a sector which is these currents plus something else, then it's like a decoupled thing. Okay, yeah. So similarly with the primary, if your primary is built, you could have in this theory a primary which is a product of a primary from the Wess-Zumino-Witten theory and the minimal model. In that case, the Sugawara construction will not correctly compute the dimension of this primary, because it only computes the part that was from the Wess-Zumino-Witten theory and not from the minimal model. Okay, but a theory in which the Sugawara construction accurately computes the stress tensor, gives you the full stress tensor, is sort of like a minimal theory. A theory where you have only the degrees of freedom associated with the current algebra and nothing else. So those are particularly interesting theories, because then you can, once you understand these, you can go ahead and study more complicated things by putting pieces of these things together. Okay, so this Sugawara construction defines a really interesting stress tensor. It has all the properties of a stress tensor, and it is natural to search for theories where that construction is the full stress tensor. Many such theories exist, like, for instance, Weisser-Minowitten theory. Okay, please go on.
Yeah, so when you are saying you are taking, let's say, sum of two theories, let's say, for the example that you took.
Just decoupled theories, yeah.
Yeah, decoupled theories. But let's say, for example, you have this minimal model and WZW model. Now, doesn't this minimal model already restricts you so much that you can't, like...
Well, you can always add two theories. Nobody can stop you. Minimal models are very restricted if you had C less than 1.
Yeah.
But the sum of the two theories will not have C less than 1. Right? The sum of the two central. Okay, what about the central charges? Suppose we had T was T Sugawara plus T minimal. Okay? The OP then of this T with itself will be exactly the form of a stress tensor, but with C equals C central, C minimal plus C Sugawara. Right? Because that singular term will add. And everything else just becomes the T's grouped together.
So it depends, like, which theories you are considering, right? What, like, I was thinking maybe sometimes you can't just have two decoupled theories.
When can you not have two decoupled theories? I think by definition of decoupling, you can always add two theories. Okay? What, you had something in mind? I feel two decoupled theories you can always add together. Who can stop you? They're decoupled. Huh. Okay, excellent. Now, what is the importance of this Sugawara construction? The Sugawara, in theories where the Sugawara construction correctly computes the stress tensor, we have great power. Because you remember that to start with, you remember that we had that the spectrum of our theory was expanded in these modules of current algebra. Okay? But now we've discovered that every current algebra primary is a Virasoro primary. Moreover, we know the scaling dimension of these primaries by this construction. We also know that every lowering operator, because the Sugawara construction has the right OP with the current, we know that when we expand J as sum over J A M by Z to the power M plus 1, M is the weight under T, the scaling dimension, the L0 weight. Okay? So we know what the scaling dimensions of all the descendants also are. So in terms of just group theory, we completely know the spectrum of a theory. If I just tell you which representations of the Kac-Moody symmetry we have, that completely determines the energy spectrum of my theory on a circle. Isn't that amazing? Okay? It's like a dream, right? That you do some symmetry and it determines dynamics. Energy is like dynamics, how things evolve in time. The symmetry is about some rotations in space. I find this amazing. I find it amazing that you have these theories where representation theory of some small extension of Lie algebras completely determines dynamics.
Can you see this again?
Yes. Okay. So let me say, I wish this board was a little nicer. If it's ever in your hands, Vipul will try to get another room. Okay.
I think this program is going on that.
Yeah, I understand. The rooms are always tough. Okay. You remember we had these modules. At the bottom of the module was a current algebra primary, one of these phi's. and then the whole module was built. We will be studying these modules in great detail. We will be writing down character formulae for it and so on. Okay, but right now the details don't matter. The whole module was built by acting with JA minus M on the primaries for M greater than 0. Okay, now JA minus M had L0 weight M, energy M. Okay, so all the states, the structure of this module is completely determined by representation theory, current algebra representation theory. Okay, it's not a free module. We argued before it's not a free module. What was the argument?
Loss cutting.
Yes, we constructed this J minus 1, and we saw that to some power it annihilated the states. So we know this is not a free module. So it's going to be a little like the modules of the minimal models. Okay, but we will just from representation theory be able to completely understand these modules, the structure of these modules. So which means more precisely we will be able to from representation theory find the characters of these representations. Okay, now character has to be weighted by something. Okay, we could for instance weight states by this level, but now we've discovered the level is same as dimension. Okay, so this tells us that we completely understand the state content of this theory graded by dimension and in fact Lie algebra quantum numbers at each dimension. Okay, we completely understand it just from representation theory. Okay, now typically our theory will have these number of representations we know is finite. Typically our theory will have a finite number of these finite representations. For instance, in Wess-Zumino-Witten theory, we will have the representations will be the following. It will turn out to be SU2 Wess-Zumino-Witten theory, all j's from 0 up to k, and left and right equal. So if you have j on left, you have j on right as well. This diagonal character. So the total number of primaries will be just k. If k was 2, it would be 2 primaries, k plus 1. So it would be 3 primaries. Sorry. Hi Naveen, I'm actually teaching a class at the moment. Can I call you in the afternoon? Yeah. Okay. Perfect. Okay. Bye. Okay. Hang on. Let me just finish this. Okay. So the full spectrum is the sum of a finite number of these modules. And the module is completely determined by representation theory. So we completely know the energy spectrum of the theory. Okay, just from symmetry. Okay, so this is a case where symmetry completely determines the theory, the dynamics of the theory. The energy spectrum means dynamics. Okay, it's like having in QCD solving the spectrum of baryons from symmetry. Would be totally amazing, right? Okay, yeah, please, now ask your question.
Yeah, so it's similar to the kind of thing we were doing in minimal models also, right?
It's similar to the kind of
dynamics, they're also like...
Yeah, the one difference there was that there was less the symmetry there was Virasoro plus unitarity. Virasoro always was about energy. I mean, it was also totally amazing. But the one distinction here is that what this is an extension of the kind of symmetry we use when we're studying rotational invariance. It's an extension of SU2. Okay, so it's kind of simple Lie algebra symmetry that we're very used to studying. We extend it in some way, and that completely determines dynamics. Okay, it's true, minimal models are also amazing. I don't want to detract from that. Okay, minimal models were also a situation where symmetry determined dynamics. Okay, yeah.
It doesn't determine all the dynamics of the theory. It's like, because OP coefficient are not here. It's like in the QCD, if you band 2.
I agree. But it determines the partition function completely. The thermal partition function. Okay, I agree. It is not completely determined. However, we will determine it using the Krishna-Examen logic of equation. Okay, in minimal models, we determined it, right? We determined OP coefficients by using the null state conditions. We have something similar here. So what I've said doesn't determine dynamics completely, but we will determine it. The one thing that is left over is what is the spectrum of the theory. That part may have some play, and it will be constrained by modular invariance. One invariant will always be the diagonal invariant I just told you about. All representations occurring exactly once and equal on left and right. This was like the is like the diagonal invariant for minimal models. So, but there are sometimes other possibilities for spectrum. So it doesn't, but up to a few choices completely determines dynamics, complete everything, including correlation functions. Yeah.
So is the limit on C here tell us something about
Okay, so this comes back to something that I briefly discussed maybe at lunch. I can't last time, but I'll come back to this. Let's take two limits. This k tilde, its smallest allowed value is 1 and its largest allowed value is infinity. First, let's go to infinity. At infinity, C is equal to 3. Okay, now 3 is very easy to interpret because one theory that implements this current algebra is Wessel-Minowitten theory. This one we discussed, right? It's a theory of a big sphere with an H flux, a big 3 sphere with an H flux. And the size of the sphere was square root k, the radius of the sphere was square root k. The density, H flux density was 1 over square root k or something like that, 1 over k is k, inversely proportional to k. In the limit k goes to infinity, the sphere becomes infinitely long, big, the H flux density goes to 0. So it becomes just sigma model on R3. And that's why it has central charge equals 3.
Why 3?
R3. So R3 is it's sigma model 3 free bosons.
Yeah,
Okay. So that it had to have central charge 3 in the limit k goes to infinity, something you could have guessed. Okay. On the other hand, let's take the other limit. K hat equals 1. In this case, we get 3 by 3. So we get 1. This is also something you know. Because when we studied the free boson theory, we studied free bosons at the self-dual radius. And that had an SU2 current algebra at k hat equals 1. But since it was a single free boson, it had C equals 1. Okay. So this interpolates between C equals 1 and C equals infinity in this way that we might have guessed on rather general grounds. Now one thing I want to say about this is as follows. This module was a current algebra module. Okay? And if you are a current algebra primary, we've just checked that you are a Virasoro primary. But the reverse is not necessarily true. Okay? You can easily be a Virasoro primary without being a current algebra primary. And in fact, if you take this module and decompose it into Virasoro representations, you will always find an infinite number of Virasoro representations. And very roughly, that this is the case, you can argue as follows. If you are being very stupid, and this is really being very stupid. Okay, but if you're being very stupid, you can estimate the growth and density of states of a current algebra module as follows. From going from one energy to the other, we have 3 options. We can act with J1 minus 1, J2 minus 1, J3 minus 1. Or you can act with J1 minus 2, J2 minus 2, J3 minus 2 and so on. When we were doing Virasoro, we only had one option. We had L minus m's. So it feels like this is like the product of 3 Virasoro characters. Right? So you might have expected its growth to be roughly one of these current algebra characters to grow like a cube of Virasoro characters. Now this is not true precisely because there are null states. Okay, and this growth will be cut down a little by null state, but it still doesn't cut it down so that cube becomes 1. So one of these modules grows much faster with energy than any particular Virasoro module, which tells you, but that can only happen if there are an infinite number of Virasoro modules, because there's a finite number of Virasoro modules. Then you go to the energy much larger than the highest Virasoro primary energy, and you grow like some coefficient times the same growth as a Virasoro module, coefficient being number of primaries. Okay, so you already see from here just the intuitive fact that there are 3 raising operators rather than 1 already makes it clear that it's much faster growth. Okay, so we will study all this in detail. We'll look at character formulae and so on, but just to have a heads up on this, each primary of current algebra always contains an infinite number of Virasoro primaries. This also tells you how powerful this symmetry is. If you were doing Virasoro representation theory, you would have no hope of solving this theory. First, it's C greater than 1. Okay, by the way, since the number of primaries is infinite, clearly it's a C greater than 1 theory. It has to be. Okay, because you get primaries at higher and higher energies, whereas there was a finite number of energies you could have in C less than 1.
But we have put an additional symmetry.
Exactly. So you've got this. You've C greater than 1. Just Virasoro representation theory tells you nothing. Okay, and even if you were somehow to do some stuff, you would have to deal with an infinite number of primaries, which is always a hard game. This sewing together of this infinite number of primaries into a single primary, into a finite number of, is what allows you to solve the theory. So it's an amazing thing. It has a large amount of symmetry, much larger than Virasoro. And in theories that have it, it's incredibly powerful. Okay, great. So we're almost done with the class. Let me just tell you about what we'll do next class. Please.
So for let's say SUN,
Yes.
Is the central charge, what will it be?
Yeah, for SUN it is a more complicated formula, but I'll try to guess it. Let's see. It will so let's try to find the interpolations. Okay. Okay. So if SUN when we go to very large K, it is sigma model on group manifold, and therefore should have central charge n square minus 1. Just because the dimensionality of SUN group manifold is n square minus 1. Okay, and when you come down to K equals 1, you can get an SUN current algebra just from n complex free fermions. Okay, in complex free fermions, real free fermions. I may be getting a factor of 2 wrong. Yeah, I think it should be n. I think it goes down all the way down to n. Just because you've got n complex free fermions, each pair of complex free fermions is half plus half, so central charge 1, and n of them. Okay, maybe n by 2. Maybe you can do a better construction, get n by 2. Let me tell you something I'm sure of. Let's do SON. Okay, let me answer SON because that's a bit easier. Okay, there n real fermions will do the job. Yeah. Okay, so it's some formula and we will work it out and get it's in terms of Casimirs and this dual Cox theta number.
No, but the interpolation will work.
Oh yes, it will always. Yeah. Okay, excellent. So one last thing I want to say before we end the class today, which is about what we're going to do next class. The fact that we have T in terms of Jj, T is roughly Jj, what that tells us is also something quite amazing. You see, T tells us it's a generator of translations. So action of T on an operator moves the operator. Whereas action of J on an operator rotated the operator. Right? So what we're going to see is that how an operator moves is determined by how it rotates. Okay?
So this we are doing on this this 2D.
Yeah. So suppose we have a plane and we've got some correlation functions, O1, On. We know how it rotates, which means we know which representation it's in. Okay? We want the action of T on this correlation function. Okay? We can determine it. We can determine it by knowing its rotation. And so we're going to find an equation of the following forms, following schematic form. Del Z of OZ1 OZN. Okay? Del Z of OZ1 Zn. I will explain this equation. That will be the point of the next class. But will be something like T1 dot Tm sum over m Z1 minus Zm on O, where these T's are representation matrices in the corresponding representations. Okay? So we will get an equation like this. Derivative of correlator is completely determined by symmetry action on correlator. This thing, which is called the conditioning homological equation, is the perhaps the key equation in the study of current algebras, and plays the role of null state equations, null state differential equations in the study of minimal models. Okay, fine. Questions, comments, otherwise end of class.
Is this something like what identity is?
It's an expression of the Sugawara stress construction. It's the fact that stress tensor is determined by product of currents. There's no reason. Once you know that, it's sort of clear that motion is determined by rotation. That's what this equation is. Okay, so next class we will study this equation and its consequences.